All right. Allow me to introduce myself again. My name is Nzala Mangobeni from Sunrand Network Engineering. I will be the chair of this second session. So allow me again once more to recognize our network manager. He's with us here, our operational manager with us, and all the Sunrand staff, as well as our speakers. You guys are welcome. Now, the following will be the rules of the House. So each speaker will be given 25 minutes to present and 5 minutes for question and answer services. The topic of our talk is the scalability and future-proofing Sunrand network infrastructure. Ladies and gentlemen, it's a road to 400 gigabits per second. Transitioning from legacy system to 400 gigabits per second technology without incurring prohibited cost. Our first speaker is from a company called Dendrite Cyber. He holds a bachelor's degree in computer sciences or computer engineering from University of Pretoria, a master's degree in electrical engineering from KU Leuven in Belgium, and a PhD in computer science, computer security, also from KU Leuven. He works as a software engineering focused on high-speed packet processing at both Neutronomy and Mira Securities. Now, his topic is as follows: high-performance packet processing with programmable data plane. Ladies and gentlemen, help me to welcome Ryan Clark on stage. Thank you.
Thank you for the introduction. As already mentioned, the topic of this talk is high-performance packet processing with programmable data planes, and my name is Ruan Leclerc. And I used to work for Netronome. I'm working for Dendrite Cyber right now. So Dendrite Cyber, we develop custom packet processing solutions by collaborating with network engineers to build systems specifically for their networks. The focus is on high-speed networks, so 100 gig fibers or faster, and we work on optimizing data feeds by filtering out specific traffic like Netflix, or removing tunnels, or filtering inside tunnels. We also look at network visibility, where we provide telemetry and statistics on the traffic inside the network. So the problem statement, the problem we're looking at, trying to address, is that uncommon header stacks are not supported by commercial off-the-shelf solutions. And packets also don't always conform to the RFC. Sometimes you see strange things on the networks, like you see UDP packets with zero checksums and strange things like that. And sometimes you need to handle those correctly. Also, data transfer rates are ever increasing, and in the past you were able to process 1 gigabits per second on using software quite easily, but doing that with a few 100 gig links is becoming really, really tricky. So commercial off-the-shelf solutions, they can be grouped into two separate categories, roughly speaking. You get the fixed function ASIC hardware. These are things like your routers, your switches, firewalls, load balancers, and packet brokers. These are very fast, but they're inflexible. They're going to remain a router is going to remain a router for the rest of his life. Also, a router will only be, or these devices will only be able to support the header stacks that they were designed to support from the very onset. So you're not going to be able to update them on the fly to do different things than what they were intended to do when the chip was produced in the factory. So they're fast in terms of high throughput, low latency, so that's great. But as I said, they're a bit inflexible. Software-based solutions include things like the Linux networking stack, OVS, Open vSwitch, XDP, Cilium, and the data plane development kit, DPDK. These solutions are flexible, but they need a lot of CPU resources, a lot of CPU cores, high memory bandwidth, and because they need a lot of cores, they require a lot of energy, and they add extra latency in terms of the packets that they process. So each packet requires a bit more time to flow from the ingress to egress. So the data plane is responsible for forwarding and manipulating network packets. And programmable data planes allow you to process custom packet headers, have custom forwarding logic, custom manipulation logic, and create custom telemetry for your network. It also provides dynamic control. You can change the rules on the fly without allowing the suffering packet loss due to the network going down. So this is a very useful thing if you're trying to mitigate against denial of service, for instance. You can figure out new rules and even add new logic that you didn't think of before on the fly. Load that up into your data plane and then don't allow the network to go down. So the key enablers for this technology is the P4 language, and we will discuss that shortly. A number of different hardware platforms, as well as some libraries, which we will also discuss soon. The advantages of using a programmable data plane is that new and custom protocols can be supported. We can adapt to new use cases, and this can all be done at a high speed, so high throughput and low latency. So this slide shows the architecture of P4 program. So P4 is this language that we use to program the data planes. It consists of three main components. On the left, you've got the programmable parser. The programmable parser, that's where you define the packet headers which you want to parse. So you will typically define things like Ethernet and IPv4 and TCP and UDP in there. But you can really program it to have any packet header type that you want. You can create your own packet header, or you can, if you've got a new header type that you need to parse and process, you can add that in there. And then from that, you can generate some metadata, which feeds into the next component, which is the programmable match action pipeline. This is basically just a set of tables, and each entry in the table has got an associated action to it. So the action logic bit, the green blocks, and this can do things like manipulate parts of the packet header, or drop a packet, or forward it to a specific port. And some of them can be done in parallel, and some of them can be done in series. And this forms a big pipeline in which all the forwarding and packet manipulation logic exists. The very last component is the programmable deparser, and what this thing basically does is it just takes the different parts of the packet header and combine it into one packet, which is then egressed on a port. Let's just discuss the data plane and control plane. The data plane, that's like the fast path. That's where things need to happen very quickly. That's where the bulk of your network traffic gets processed. So this is to do with the processing and the forwarding of packets based on rules. And like I showed in the previous slide, the blue blocks, that's where we've got our lookup tables, and those are where we program our rules. So here we're doing forwarding and filtering and encapsulation, decapsulation, and generating telemetry. It's high speed, low latency, but we can't do any buffering inside the data plane. If we want to do anything complicated, we send the packet to the control plane, and the control plane kind of acts like it's like the slow path, and this is where the decision making and traffic control is done. Think about network management, configuration, and complex processing. So this is lower speed, higher latency. Buffering is possible here, so you can do complicated things like TCP reassembly and reassembling of fragments and things like that. So if the data plane doesn't understand, if you've got some rules and you've got a system that learns rules on the fly, and it doesn't understand how to handle a specific packet, it can forward it to the control plane. The control plane can make a decision or can parse this thing, make a decision based on the contents of this packet, and then install a rule inside the data plane so next time it sees that header stack, it knows how to process that packet. So we're going to look at 3 different types of programmable data plane platforms: the Smart NIC or the Smart Network Card, the programmable switch, as well as the Data Plane Development Kit, which is a library for doing packet processing in software. So on this slide, I'm showing an AMD Alveo V80 Smart Network Card. It's got 4 200 gig links, 4 200 gig ports. It's got a large amount of field programmable gate array fabric, so programmable fabric that we can use. We can take our P4 code and compile it for this NIC and run it on there. It's also got two ARM cores, so you can do your control plane can exist in many different places. So your control plane can exist on the Smart NIC, on these ARM cores. If you need to do a bit more heavy lifting, you can do the same thing on the CPU, so then communicate to the NIC via the PCI Express. But your control plane can also exist outside of this specific host. You can have a control plane on another node in the network, for instance. So the players in this space is AMD, Intel, Napatech, and Netronome, and I'm a former employee of Netronome. On this slide, I show you a programmable switch. So this is kind of similar to a Smart NIC, but it's got a lot more ports. In this case, I'm showing you an Intel Tofino 2 programmable switch. It's got 32 400 gig ports, which gives you a total of 12.8 terabits per second that you can process. It's got only a 4-core Intel CPU that is used as the control plane. On this slide, I'm showing you just Linux without DPDK versus Linux with DPDK. So if you just doing plain packet processing through the Linux kernel, then there's a limit on the speed at which you can process packets. So you're getting about 1 gigabits per second per CPU core. Reason is you need to work through the Linux kernel, and there are context switches that happen when you receive the packets from the kernel to the user space. So each time you need to read, you're going through a context switch, and there are copies and things that happen. Memory has to be copied. So the idea here is on the kernel, you've got a driver, and the driver communicates to the network controller, but then the Linux kernel also gives you like a whole ecosystem of tools to create sockets and do things like that. So that's awesome. It abstracts a lot of things away from you. It makes your life easy. But you can go much far. If you need to, like a lot of performance, you cannot suffer all those context switches and all those copies and things. You want to communicate directly with your NIC. And so there's a library called DPDK, Data Plane Development Kit it's called, that can communicate directly with your NIC. But the caveat is then you need to go and build the networking stack, all the complicated processing. You need to build that on top of this library. And this can give you like a 10x increase in performance, provided that you do a lot of like smart tricks and things to make sure that you can run as fast as possible. So I'm going to run you through a case study of MPLS decapsulation POC that we did recently. The goal of MPLS decapsulation is to remove the MPLS headers so that the downstream tools can understand the packets that it receives. So in this case, the downstream tool did not have the capabilities of understanding MPLS, and so we stripped or removed, we decapsulated the MPLS from these packets. But the problem with MPLS decapsulation is that inside the MPLS header, it doesn't say what is following. So in let's look at what, yes. Okay, so in this case, we've got Ethernet, then we've got a MPLS header on top of Ethernet, and after that, we've got IPv6. But like I said, this header doesn't say that the next thing to follow is IPv6. So if we want to decapsulate, then we need to go and update this Ethernet header's ether type such that it says IPv6 follows. So that's just the overview of MPLS decapsulation. So there are many different header combinations that are possible. You could have Ethernet, then MPLS, then IPv4 or IPv6 or Ethernet, and then some more things. You could have Ethernet, then MPLS, then a pseudo-wire control word. And then, similar to the previous one, IPv4, IPv6, or Ethernet. You could also have Ethernet, then IPv4 or IPv6, then MPLS. And you could even have a scenario where you have some MPLS labels and maybe IPv4 or some other things, and then MPLS again. So you have this like nested like MPLS situation. So the commercial off-the-shelf packet broker solutions products that we looked at, they were not able to always properly decapsulate MPLS. The reason being is they made some assumptions on whatever follows the MPLS. They made assumptions on what is next based on the first nibble that follows the MPLS header. So when the first nibble is a 4, they assume it's IPv4. If the first nibble is a 6, they assume it's IPv6. And if the first nibble is a 0, they assume it's Ethernet. However, this is not always the case, because the serial wire control word, that can also start with a 0. And if you would assume it's Ethernet and you update the ether type, then you wouldn't, or let's say, yeah, you wouldn't be able to strip it properly if there's a serial wire control word here, because then the first thing in the stack would be a serial wire control word. You would also need to remove the serial wire control word. So it's kind of a tricky thing. Same thing with MAC addresses. In the super long time ago, MAC addresses didn't start with a 4 or a 6, but now things have changed and MAC addresses can start with a 4 or a 6. So these two cases, that's not always correct. Also, the commercial off-the-shelf solutions we looked at couldn't process more than 6 MPLS labels, and they had trouble with nested MPLS, and also they didn't handle fragmented MPLS over IPv4 traffic properly. So the solution we came up with is to learn decapsulation rules through speculative parsing. This diagram I'm showing you here, that is to do with how the packet is processed inside the data plane. In the next slide, I'll show you how we do the speculative parsing. So the idea is we receive a packet, we check if it contains MPLS. If it doesn't, it gets forwarded out. But if it does, we look up a stripping rule in the table. If the lookup was successful, we apply that stripping rule. If the lookup's not successful, we mirror the packet to the control plane so that we can learn the stripping rule inside the control plane. So we can do the complex processing over there. The lookup key we used was MAC address, or the MAC addresses, the VLAN IDs, and the MPLS labels to uniquely identify that header stack that we want to strip. So like I said, we're doing, so this is in the control plane. And the idea here is to do speculative parsing, and the key concept is to add a rule to the table if checksum validation has succeeded. Because if we can verify checksum after the MPLS, it means we've parsed correctly, which means everything was good and we can install a new rule. So we first parse our MPLS, then we've got our speculative parsing step, and here, let's say we try and parse IPv4. If the IPv4 parsing was, we then try to verify the checksum, and if the checksum is verified, great. We install a rule. However, if we couldn't verify the checksum, and the checksum was wrong, either the packet was corrupted, or more likely, we didn't parse it properly. So the next thing we'll do then is we try and parse it, the thing after MPLS as Ethernet, and maybe then IPv4, and then verify the checksum. So there's like a whole tree, there's a whole different like graphs, a path that can be taken through this graph in order to try and verify the checksum. In the end, hopefully we get to that point. If not, we just drop the packet and continue processing the next packet that we receive. So the achievements of this POCs, we were able to build something in 3 months with a team of 3 people. So we could rapidly prototype this sort of design. We were better than the commercial off-the-shelf solutions because we could correctly decapsulate all of the network traffic. We did this over 100 gig links, 32, and we used 32 ports on a programmable switch. So in this case, we used the Intel Tofino 1 platform, but we could have used the Intel Tofino 2, and then we would have gotten even more throughput. And yeah, the P4 language, it's like kind of platform agnostic, or it tries to be as much as possible. So we could easily take our P4 code and compile that and run that on a Intel Tofino 2. We didn't need any rules for IPv4 over MPLS, and we also managed the updating of rules. So we check where the rules are used, and because MPLS labels get added and removed all the time on these networks, and so we have to remove, like, make space for learning new rules in our table. And that's where this aging comes from. Also, we're able to detect network changes. So if there's changes if the network changes, like if for a specific set of MPLS labels, if the network changes, we can detect that and then change the stripping rules such that we can keep on decapsulating this correctly. So the summary of the takeaways is that programmable data planes are flexible and efficient, and feature directions that we're working on is deduplication, network visibility, so things like NetFlow and IPFix, also telemetry, as well as a next generation packet broker. That concludes my talk. Are there any questions?
Any questions? Yes.
Thank you very much for the presentation. I just want to find out, I'm also in the space of programmable data, like programmable data planes, in the software-defined network environment. Will you be kind to borrow me this development kit so to also run some tests on it?
We should have a discussion offline. Yeah.
Thank you.
Okay. Yes.
Are you asking about decapsulating other protocols or just like parsing them? Yeah, certainly. I mean, we didn't like go and check whether other commercial off-the-shelf solutions decapsulate that traffic correctly. It's much simpler to decapsulate other types of traffic. So they probably do it correctly. We just had a customer that has had a need for doing this things, MPLS decapsulation specifically, and so that's why we targeted that. But certainly that's possible, yes.
So the idea is you don't want to lose the structure of the traffic when you decapsulate. So in those circumstances, it might be useful to do it using this appliance.
All right. I think one more from me. With regards to load balancing and traffic shaping, how do you see the programmable data plane optimizing? How will you handle the traffic flow on that type of instance?
Yeah, so it's certainly useful for load balancing. My initial, immediate thought is you can then, because you can parse to a really deep inside these tunnel headers, you are much better equipped to then load balance the traffic, because you want to be able to parse to the inner headers such that you get the maximum differences in the headers, the maximum entropy in the headers. So if you're only load balancing on the outer Ethernet addresses, then you're not going to have a very good load balancer. But yeah, certainly with this solution, you will definitely be able to do that. Yeah.
Maybe also just as some background, one of the largest users of this programmable data plane technology is ByteDance, the guys behind TikTok, and they use it for load balancing.
Yes, Johan?
How do you specify what you're interested in, and how does the output look? Is it command line stuff? Do you put it in a database? Do you do a visual display? How do you select the stuff you're interested in? How do you get the outputs afterwards?
So in this case, we just built a MPLS decapsulation solution, right? So the input is 100 gigs. The output is probably a little bit less than 100 gigs because we've stripped off some of the headers.
Data that you're interested in specific data, how do you visualize it somehow? Or do you put it in a database?
We're running Prometheus and Grafana dashboards, and so we do things like saying these header stacks have got this, this percentage of the traffic has got these header stacks, and we do things like we can say this amount of traffic is running on these ports and things like that. But that's just for the operator of the device to see that it's still more or less doing what it's supposed to. It's more for monitoring the health of the device rather than anything else. Don't know if it answers your question.
Yeah, I think you get to NetFlow, if it's that kind of information, you would store it in some form of large-scale data storage.
Any question?
So how does this technology enhance the packet processing for the network devices like your routers and switches?
I'm sorry, I didn't hear the last one.
I'm asking, so how does this technology enhances the performance, packet processing performance for the network devices like your routers and switches?
Well, it's just highly programmable, right? So you can take some commercial off-the-shelf solutions and use that, and it can do whatever you want it to do, but that'll be fixed function, and that's going to stay. It's going to fulfill the same role as you buy it, and it does this one thing, and it does it pretty well. But our solution, our whole aim is to develop custom solutions. So we capture a small percentage of the market. We're not like the guys who build the thing that like 95% of the whole world uses basically. So yeah, I don't know if that answers your question.
Where fixed routers and switches, they process standard header stacks. So they're looking for an Ethernet, VLAN, IP header stack. But so they can filter and load balance, for example, on IP or on a 5-tuple. But now, let's say in the case with MPLS encapsulation, they also don't necessarily know what's after the MPLS. So they can maybe load balance on the MPLS, but not what's in the contents. So if you can smartly decapsulate your header, you can get to the stuff that you actually want to load balance on.
So we can help those things do what they're designed to do in a more efficient fashion, despite you getting all kinds of weird and strange traffic protocol studies.
Okay. Any other question? This seems to be interesting. Right. Thank you very much. Thanks, Ryan. Thanks. That was massive. Just get yourself. Okay. While